So today we're going to be modeling an exponential function given 2 points. Now we're also not just modeling an exponential function given any 2 points, we're using 2 points that are what we call consecutive points. Now all consecutive means is they're one right after the other. You'll notice each of our problems that we're going to be doing going forward, I have a 7, then an 8, I have a 5 and a 6, a 4, then a 5, a 12, and then a 13. These points are one right after each other. That allows us to find the growth or decay factor very quickly, and we don't need to create a system of equations to do that. So without further ado, let's go ahead and jump into the first one and kind of keep an eye on our steps on this first one to make sure we're following the right order of the right procedural order. So we're going to create an exponential model for the given scenarios, and if a and b are not whole numbers, we're going to round them to the nearest tenth. So to find the growth factor, I want to know what am I multiplying by to get from this point to this point. And the easy way to do that is to take the second y value and divide it by the first y value. So what I'm going to do is I'm going to say, okay, if this is y2 and this is y1, in order to find my b value, I'm going to say b is equal to whatever 39,366 is divided by 13,122. So what I'm going to do is I'm going to go ahead and I'm going to take those, I'm going to pop out my handy dandy calculator. I'm going to say, what is 39,366 divided by 13,122? I'll get 3. So my b is equal to 3. And I'm going to save that as an important point. The next step is I need to find the starting point. Remember that the model that we're using is y equals a times b to the power of x. We just found b, now I need to find out where we start. Whatever's going on in this scenario, I'm multiplying by 3 every single time. Where do I start? Now what I could do is I could divide by 3 going back, going back, going back, going back. But one of the common problems that students often forget is that our starting point isn't when b equals 1. Oftentimes they'll divide back until they hit 1 comma something. Our starting point is when b is, or when not when b is 1, when x is 1. Our starting point is when x is 0. Where does it cross the y-axis? And so the easiest way to do that is instead of dividing, or if it was a fraction, multiplying, is we'll just plug in some values. So I need to plug in values to y equals a times b to the power of x. So what I need is I need to figure out what b is, what y, and what x is. And lo and behold, I'm given 2 possible choices. So I'm going to use the smaller of the 2 for no reason other than that I like small numbers. So 13,122 is equal to whatever that starting value is times b, which we know our b value here as 3, to the power of x. Well, the x attached to 13,122 is 7. So we're going to go ahead and say, okay, 3 to the 7th power is going to be, let's take a look at what is 3 to the 7th power. We get 2,187. So 13,122 is 2,187a. The next thing is I'm going to divide both sides by 2,187. So whatever 13,122 divided by 2,187. And I'll get 6. Okay, that's my second important point. After that, I'm going to go ahead, I'm going to model by saying, hey, my final answer, let's go ahead and write this in green, is equal to y. My a value is 6 times my b value, which is 3 raised to the x power. And there we go. We have successfully modeled a function, or we created an exponential model. We haven't necessarily created a function for this. This is just an equation. And our a and our b were whole numbers, so we didn't need to worry about rounding them. So let's go ahead and let's try that again for number 3. So our first step is we notice that these are consecutive numbers, 4, then 5. So I'm going to go ahead and say, okay, my b value is equal to my second divided by my first. So 2150 divided by 1200. And so if I plug that into my calculator, what I'm going to see is the fact that I get 1.79 repeating. So now what it says is it says round a and b to the nearest tenth. So what I'm going to do is I'm going to say, hey, b is equivalent to 1.79. Now, the problem is I rounded this to the nearest tenth. I don't want to use the rounded value to find what my a is because that would be a rounding error leading into something else. So what I'm going to do is on my calculator, I'm going to store this value. And without changing anything, I'm going to hit a few buttons. I'm going to hit store this, and it says take the answer and save it. As a b, I'm going to hit alpha b. Enter. Enter. Oh, could go to. There we go. Third tries the charm. I typed a negative sign after b. So I've got answer has been stored as b. So next time I bring up alpha b, I get that number. I don't need to worry about saving it for later use. That later use is about to come up here in the second part. I need to model this function. So I have y equals a times b to the power of x. I'm going to use the smaller x and y. So 1200 equals whatever a is times our b of 1.79 to the power of 4. So I went ahead and used this first point to plug that in. Now 1.79 to the 4th power, remember, we're trying to avoid any sort of rounding errors here. So I'm going to take b and raise it to the 4th power, 10.304. And then I'm going to take that number without clearing it, 1200, divided by my answer is going to give me 116.45. Now, the reason why we did this, also before we continue any further, my a value, I'm going to store this again as a value within my calculator. So if I know what b is, I'm going to store this as alpha a, so that way I can use that later on. Let's say I didn't store that value in my calculator and I tried to figure out what a is using just 1.79. So let's say 1.79 raised to the 4th power is 10.2. I already see the fact that I'm a little off. And if I take 1200 and I divide that by, let's say I'm rounding to the nearest tenth again because that's what I want to do, divided by 10.26, I'd get 116.95. So I'm almost half a unit off, which doesn't seem like a lot, but if we're half a unit off and these are small numbers, let's say these are in millions of dollars, it's going to be a big deal. If we're trying to figure out what is the proper dosage of medicine we want to give somebody, that half of a unit might be enough to kill them. So we don't want to get in the habit of rounding until we get our answer, just because we don't know what context this is going to give. But I do know my final answer is y is going to be equal to 116.45 times b, which is 1.79, raised to the xth power. There we go. Awesome. And so now why don't you go ahead and try the last one. Try number 5. Figure out what your b value is. Remember, don't round, or if you do, save the value without clearing it. And then use that to find your a, and then you've created your model. Unpause it when you're done and see all you did. Okay. So now that you've had a shot of this, let's go ahead and take a peek. I know my b value is equal to y2 divided by y1. I have 768 divided by negative 192. I know my b value is going to be equal to, let's go ahead and check this out. Go ahead and clear all this. So I have 768 divided by negative 192, and I get negative 4. Okay. I don't need to store that. I can just go ahead and jump off into the next one. Y equals a times b to the power of x, and I'm going to use this one. So negative 192 is equivalent to a times whatever b is raised to the 3rd power, and that's going to be negative 4. Well, negative 4 raised to the third power, we could probably do this in our heads. 4 by 4 is 16, times 4 is going to be 64. But just to make sure, let's go ahead and raise negative 4 raised to the third power, negative 64. The other thing that I wanted to point out is that when we raise negative 4 to the third power, you want to be careful not to just type in negative 4 raised to the third power, because your calculator is going to read this as exponents first, 4 raised to the third power, and then make the answer negative. You'll still get a 64 on this, but if I'd used the other one, we'll notice that negative 4 raised to the fourth power versus negative 4 raised to the fourth power, I get two different signages. Why? Because the calculator doesn't include the negative unless you tell it to. So you want to be very careful when you're typing numbers and raising them to powers if there's a negative involved. Always include parentheses if you can include them. Okay, so I get my negative 64a. Not quite done with this. So I'm going to pull this back out and say whatever 192 is divided by negative 64. And we'll get a positive 3. And so that's all that we need to go ahead and answer this. We'll say, okay, I have my A, my B. So y is equal to 3. We're multiplying that 3 times the number negative 4, however many times we want. And there we go. Negative 4. Perfect. And now what that's going to do, that's going to bring us to some of the scenarios that we'd like to look at on the back. So what we've got going on here is we have some, exactly what we said, some scenarios, some real life applications of what's going on. We have some scientists measuring bacterial growth. After 5 hours, there are 6,250 colonies. 1 hour later, there are 31,250 colonies. Create an exponential model of the scenario. So what I notice is that 5 hours and 1 hour later, I have consecutive hours here. So I can almost treat this like a coordinate, which means that I can say my B value is going to be equal to whatever that divided by that is, and that will give me my hourly growth. So 31,250 divided by 6,250. So my B is going to be equal to, let's go ahead and check this out. So we have, clear this, 31,250 divided by 6,250. I'll get 5. Actually, let's zoom in so we can get a little bit of both. So I got a B value of 5. Awesome. Next, I'm going to use that as part of my model. I'm going to use this as my X and this as my Y. So 6,250 is the result of some unknown starting value, multiplying by 5 every hour after 5 hours. So I have 5 raised to the 5th power is going to be 3,125. A. And then I'm going to say, okay, what is 6,250 divided by 3,125? So my A value is 2. That's all the information we need to plug it into our model. So Y is equal to a starting value of 2. So it looks like at the beginning of this experiment, there were only 2 bacterial colonies. And after every hour, they not doubled, not tripled, not quadrupled, but they pentupled, I believe is the expression. They multiplied by 5. So those 2 became 10, those 10 became 50, those 50 became 250, and then after 5 hours, we had a lot of bacteria going on here. Perfect. So let's take a look at one more. We have cockroaches are finding a food source, and after 13 days into their feast, the colony has grown by 45 roaches over the past day to 795. We're going to create an exponential model for the situation. So what we got going on here is they didn't quite give us both sets of points. They did say that 13 days into the feast, the colony has grown by 45 roaches to this number. So what I can imply that at 13 days, we have 795 roaches. And we know that over the past day, so that means at 12 days, one day ago, they were 45 less. So I'm assuming there were 750 roaches yesterday, or at the 12th day. And so that's all the information I need to really go ahead and answer this. Let's go ahead and get this set up. Say B is equal to my new value, which is 795 over 750. Let's take a look at this. So 795 divided by 750 is equal to 1.06. Perfect. Don't need to store that because it's exact. Let's come over here and say, okay, y is equal to a times b to the power of x. And I'm going to use, let's see, 13 days we have, so it looks like days are going to add roaches. So I'm going to say my days is my x and my 795 is my y. In this case, I picked the larger number, not because I meant to, just because I had already written it at this point. You could easily plug in 750 and 12, and you'll still get whatever the answer is that we're going to get, you'll get the same thing. So let's go ahead and figure that out. So I'm going to take 1.06, and I'm going to raise 1.06 to the 13th power. Get that, and I'm going to take 795 and divide it by that number. And I'll get 372.72. Now I am going to store that as my alpha A. If I were deemed to use that in an example, I don't really need to right now, but I know A is roughly equal to 372.7, and we're rounding this, so 7.3. Okay. And now, actually I misspoke. Because we're rounding this, A is going to say we're starting with part of a cockroach. So we're going to have to make a judgment call here. Do we want to say that on the first day or on the 0th day we had 372 cockroaches or 373 cockroaches? There's not really a wrong answer to this, but I'm going to say my expression is equal to, I'm going to go with 372 times 1.06 raised to the xth power. And I'm going to put that we rounded down to not assume a larger starting population. Do you need to necessarily put that? Not really, but in this case, we're like, hey, we can't start with a decimal of a cockroach. I don't know what's going on. Maybe that cockroach is being born, but I'm going to go ahead and round down to not assume too large of a starting population, because otherwise we might need to call in the exterminator faster than we need to. So, that being said, why don't you go ahead and try the last one? The last one's a little bit of a doozy, because it's got a little bit of something in there that you'll notice after you get it started. So go ahead and pause the video, unpause it when you're done, and see how well you did. Okay, so let's see how well you did on that. We have a collapsing star that produced gravitational waves that measured 10,240 units above normal background 10 minutes after collapse. And then 11 minutes after this star is collapsed, the gravitational waves measured 20,480 below normal background. Okay, so we have a number that it looks like these waves are waving, and then at 10 minutes we're measuring something that's like at a peak, and at 11 minutes we're measuring something that's a trough, or maybe somewhere there in between. Let's go ahead and see if we can't figure that out. So at 10 minutes, we were at 10 to 40, and then at 11 minutes, we were at 2480. But we're also below the normal background, so I'm going to make that a negative 2480. And that's really all we need to answer this. Let's go ahead and figure out what our b is. So our b is the most recent unit, so negative 20, 480 over 10 to 40. And I can just look at that and say, hey, my b is equal to negative 2. I don't need a calculator to knock this one out. But let's pop this off into the next step and see if we might need one. Okay. I'm going to say I'm going to use the lower one, unlike the last time. My y value, I'm going to assume I can pick the time, and that will give me how far the waves are above and below. So 10,240 is equal to a times my b of negative 2 raised to the 10th power. Now this I will need a calculator because I don't know offhand what 2 to the 10th power is, let alone negative 2 to the 10th power. So let's go ahead and figure that out. So clear all this. So we get negative 2, remember include it in parentheses so that we don't assume a negative error there, raised to the 10th power. And we'll get 10 to 40 is equal to 1024a. Again, if I hadn't thought of keeping that negative 2 raised to the 10th power would have given us a negative number, and that would have thrown off our metric. This one also right here, I noticed that this is probably going to be equal to 10, but just to make sure, 10,240 divided by 1,024 is equal to 10. Yep, we just went ahead and removed the 0. So we have our b and we have our a. And to model that, we have y is equal to starting value of 10 times a rate of negative 2 raised to the x power. So what we see here is that every minute the wave is going up and then the wave is dipping back down. So I'm assuming this is whatever the normal range would be, is right there in the middle, and we're detecting the waves going above and below that point. It looks like not only are they going above and below that point, but they're getting bigger. So this collapse does not mean good news for us. And there we go.